Hello, everyone, and welcome to this micromaterials webinar. It'd be great for you all to just say hello in the chat and let us know where you're joining from, just to make sure you can hear me loud and clear. My name is Dr. Sam McMaster. I will be your host for today's webinar from Surface Ventures, and I'll just be acting as a host. Great. It looks like people can hear me from CNL, Austria, UK, Stoke-on-Trent. Fantastic. Great. Glad to have you all with us. Just a quick note for if you're having any issues seeing me, please try to refresh your browser, or please try a different type of browser. So continuing with the introduction. So today's webinar will go for around 60 minutes. We'll be having our speaker, Dr. Abheepsit Raturi, on stage first, after which Andrew Bird from Micromaterials will be speaking on the nanotest equipment, and then we will have our question and answer session. An attendance certificate will be available for this event, which I will release later in the event. Additionally, we will be releasing some handouts and some poll questions from Micromaterials to learn a bit more about you, and also just to provide some further information about Micromaterials equipment. Okay, so now moving on to the introduction for our speaker. Dr. Abheepsit Raturi successfully completed his PhD in materials engineering from the Indian Institute of Technology in Kanpur, India. Dr. Raturi currently serves as a research fellow at the Tel Aviv University in Israel. His primary research focus is on exploring methodologies for alloys, designing for high entropy alloys, and understanding the material mechanics across different length scales, including nano and micromechanics. His expertise spans a diverse range of areas, including modeling and simulation of alloy design and plastic deformation processes, structure property correlations, micro and nanomechanics studies through indentation, thermomechanical processing, and crystallographic texture analysis, additive manufacturing, severe plastic deformation analysis, and high pressure torsion. So without further ado, let's welcome our speaker on stage, and then we'll get his screen share set up. Okay, please come on stage now, Dr. Raturi.
Sam, for such an introduction.
Great to have you with us.
So, tell me when we can start.
Okay, so you just go ahead and set up your screen share. I'll just check that I can see it. Once that's there, we're ready to go.
So now I can share my screen. Let me do it. Is it visible?
It is now, yes. So,
So
fantastic. Take it away.
Yeah. So thank you everyone to joining this webinar and to listen to the talk. So I will start. I'm talking about the unique temperature-dependent mechanical behavior of this refractory entropy alloy, and with the nanoindentation testing and the atomic simulation. I have done this work when I was in IIT Kanpur, and we took the help of Micromaterials. So if you talk about the ultra high temperature application, especially in the space exploration, you see that rocket nozzle or the satellite components, they are subjected to extremely high temperature gradient and thermal stresses. So the environmental conditions are very harsh for this component, so they have to subjected to very high stresses. Also, if you see the fusion reactor and the plasma facing material, the component in the fusion reactor and the plasma facing material, the plasma facing component, they are subjected to very high energy flux of high energy particles like neutron and the hydrogen and helium. So the conventional material used in the normal condition cannot be used in this particular application of ultra high temperature. However, the refractory metals, which is very high melting point, can be used in this particular application because of they have high melting point and high mechanical property. However, they have their own disadvantage, like the deformability is low, and they have very poor oxidation resistance. So in order to deal some of these problems, there's new designing methodology was developed, where 5 elements or more than 5 elements are mixed in an equal or near equal proportion to form a alloy. And since the developed alloy has a very high configuration entropy, so they generally call as the high entropy alloy. So what is the one of the most important part of this the high entropy alloy design concept, that along with the A's, we can explore the centric space of the phase diagram also, and we have more options to develop this alloy. So similarly, in same way, the high entropy alloy designing was used, and the refractory high entropy alloy was developed, where the refractory metals are the principal element. And one of the initial developed refractory high entropy alloy, which was molybdenum niobium tantalum tungsten alloy, it was when it was tested, it showed a very high remarkable property in the temperature range of if you see the in the temperature range of 1200 degrees Kelvin to 200 Kelvin 2000 Kelvin, it show a remarkable property in comparison to the conventionally used high temperature alloy like Inconel 78 and the Haste alloy. So they have better property in comparison to the conventional alloy, but they have their own problem, like they have deformability is low, and so they cannot be used directly as a structural metal in this compound. So there are some R&D challenges in this alloy, and I'm going to discuss about these challenges in this upcoming slide. So there are this R&D challenges of on this refractory entropy alloy. One thing is the phase stability at high temperature. So since they are new alloy, they their phase stability at high temperature need to be tested, whether they are forming the different phases or it is forming a single phase structure. One more thing, they have the fabrication. The fabrication is also challenging for them along, because they have poor ductility or deformability at room temperature. The deformation, their processing will be difficult. Also, the mechanical property and the deformation behavior, since they are is new and they have high configuration entropy, the mechanical property and deformation behavior need to be tested and checked. So deal with this in order to deal these R&D challenges, uh, this is our strategy, that we have used high entropy alloy design concept, since it was already shown that this alloy designing concept has shown make a alloy with so a better property than conventional alloy. So we have used this designing methodology, and to predict the phase stability at high temperature or even at room temperature, we have used the CalFED modeling. CalFED modeling is state-of-art technology based on the thermodynamic principle. So it is very robust method to predict the phase stability. And to deal with the fabrication process, we have used the vacuum arc melting process, and to study the deformation behavior, we deal with we use the high temperature nanoindentation testing, which is robust and also require very small amount of material. Since because they are new material, we have also limited with the amount of material which we have. And to understand the deformation behavior in the atomistic level, we have used the ab initio molecular dynamic simulation, which will give accuracy and also able to simulate a decent amount of atoms in the superset. So before going deep into the CalFED modeling, I want to discuss with the thermodynamics of high entropy alloy and also with the CalFED modeling. So the CalFED models work on the principle of minimizing Gibbs free energy. So if you see that Gibbs free energy of any phases can be defined as a summation of Gibbs free energy of individual constant phases, the ideal Gibbs free energy of mixing, and the excess Gibbs free energy of this excess Gibbs free. So, but if you see that while considering our modeling, we consider that pure element as a standard state. So since the pure element as a standard state, so the constituent Gibbs free energy of the constant phases are we consider as 0, and to predict the Gibbs energy of phases, we considering the ideal mixing of this alloy and ideal mixing of alloy with the Gibbs phase energy, and since this ideal mixing of Gibbs phase energy give equal to the configuration entropy, we have directly used this term. So at the end, the Gibbs free energy will equal to the excess enthalpy minus T times delta S entropy due to ideal mixing, which is equal to configuration entropy plus entropy due to the excess thing. So to model this the Gibbs free energy of phases, there are different model like regular solution model and sub-regular solution model. So in case of regular solution model, the atom are considered as random distributed, and the enthalpy of solid solution. If you see this, SS means solid solution of phase, solid solution phase. So when see the regular solution model, it shows that the enthalpy of solid solution phase is not equal to 0, but slightly deviation from this 0 value. So and the configuration entropy, the entropy of solid solution into times the temperature, it's so symmetric about the equiatomic composition. So in case of regular solution model, the enthalpy of phases, you will get this symmetric about the equiatomic position. But when you go to the sub-regular solution model, you see that although the T(S), which is temperature multiplied by the entropy, is symmetric about the equiatomic composition, but the enthalpy is not symmetric about the equiatomic position, because when there is a ordering or the phase separation, the value is a little bit changed, and this is not dependent upon the alloy composition. So the enthalpy is not symmetric, so that leads to the Gibbs energy is also not symmetric about the equiatomic composition. Why I'm focusing more, emphasizing more on that it is not symmetric about equiatomic composition, because earlier it was thought that the equiatomic composition will have high configuration entropy, and it will lead to the high stability of this equiatomic phase. But we know with the subregular solution model that even the non-equiatomic composition can have a lower Gibbs free energy compared to the equiatomic composition, so they can have a better thermal stability. And also I want to discuss with the CalFET modeling approach. So how it will work, how the background of things will work. Like it contains the description of the binary and ternary phases. What the meaning of description? I will say the description in the form of theoretical, where the quantum mechanics and statics thermodynamics parameters are taken, and from the experimentals, the DTA calorimeter, XAD, and the metallography, some parameters are taken from there, and the information from the theoretical and the experimental information are used in a model. And if you see what is the model is containing some thermodynamic function, where the enthalpy, entropy, and the Gibbs free energy as considering as a temperature function of temperature, pressure, and elements, and predicting this model from the binary and ternary diagram, the ternary phases, it were extrapolated to the higher order system like quaternary and the quinary, and their understanding the phase diagram was made, and their understanding was developed, and they was applied into the real application. So so we jump to our CalFET modeling approach. So in this, what we have done in the high entropy alloy designing concept, we have taken 9 element, and like this all are refractory metals. If you see this 9 refractory metals, and from this 9 refractory metals, we have selected 5 metals at a time, like that, because we have want to make a quinary alloy, and initially we take all the principal element in equiatomic composition. That means their chemical composition are in equal proportion, and from that way, we from the 9 refractory metals, we develop a quinary alloy, which is from the 9 we have selected 5, so it will become 9C5. It's equal to 126 equiatomic combination. So from 126 equiatomic combination, we have tested them for phase stability. We predicted their phase stability through a MATLAB code, and compiled with the thermocal, and we find out from from 126 equiatomic combination, we got only two best alloys, which is molybdenum, niobium, vanadium, tantalum, and tungsten phase, the alloy, and the chromium, molybdenum, tungsten, rhenium, vanadium alloy. These two alloy are having a large thermal stability of phase, like this is single phase BCC phase here, and this phase is stable quite over a quite temperature range. You see from 700 Kelvin to almost their melting point, they are stable. And even also in this chromium, molybdenum, tungsten, rhenium, and vanadium alloy, the single phase, the BCC phase, is stable from their 1000 Kelvin to up to their melting point. But if you see that even this, I'm saying that this phase is stable from the melting point to 700 or 1000 Kelvin, but it's transformed into the other phases when the temperature is lower than the 700 Kelvin or 1000 Kelvin. So the equiatomic alloy we have tested. So we jump to the non-equiatomic alloy composition in the search of having an alloy which show a large thermal stability over a wide temperature. So we since we got this two equiatomic alloy which is showing good results in equiatomic combustion, so we tested the non-equiatomic combustion of these alloy. So what does it mean over non-equiatomic combustion? Earlier in equiatomic combustion we are saying that all the principal element had chemical composition equal. Now we are varying the composition of individual element from 5 to 35 from 5% to 35% and generating a different alloy. And in this way, when we are varying composition of each element in the alloy, we got a 1451 alloy of each equiatomic alloy. So predict their thermal stability. We have done the thermal stability in the we have shown the thermal stability of the phases in the form of a ternary phase diagram. If you can see here, we have shown the ternary phase diagram. So it's pseudo-ternary phase diagram in 1000 Kelvin, 600, 400 Kelvin. Now to how to predict how to understand this phase diagram. So if you see this, there's a different colors here, and the red color is showing those alloy which is giving 100% single phase structure. So if it is showing a red color, it's showing that alloy is going 100% single phase structure. Now if you see that at 1000 Kelvin, this 1000 Kelvin, this there are some alloy, I think 82% I will say the alloy is showing single phase structure. But when you go to the lower temperature, 600 Kelvin and 400 Kelvin, that is very less alloy, or I will say no alloy is showing single phase structure. But so we tested the another composition, the molybdenum, tantalum, vanadium, tungsten, and we see that all the alloy is showing single phase BCC structure at 1000 Kelvin. And even when we are moving from 600, we are going to 600, and even the 400 Kelvin, we saw some alloy is showing single phase structure in this temperature range up to a 400 Kelvin. So we can say that obviously is showing a single phase structure 400 Kelvin, and these are also showing 1000 Kelvin, and even at a high temperature, this is going to show a single phase structure. So these alloy which is showing single phase structure 400 Kelvin are showing a single phase for a whole temperature range from their 400 Kelvin to the melting point. So we got some alloy which is showing a single phase structure from over a large temperature range. So once we got this result from the CalFET, we want to validate this result with the experimental technique, and we have used the vacuum arc melting to form this alloy, prepare this alloy, and done the XRD testing. So XRD testing, we have done the XRD testing on the more than 6 and 7 alloy, and we find out all the source of single phase structure. Also in the micrograph structure in the SEM, they show a dendrite structure, but we do not see any traces of second phase particle. We have done the TM analysis and the bright field and the SADB pattern, and also in the SADB pattern we got single structure, the reflection from the single BCC structure from 111 zone axis, and yeah, that's it, showing that it is a single phase structure. uh, After computing, after validating that now it's final that this alloy as showing a single phase structure, we tested their mechanical property and find out that the macro hardness and the elastic modulus are showing better property in comparison to even the equiatomic counterpart. So we can say that obviously that the non-equiatomic alloy is showing better phase stability, and also when we tested their mechanical property, it showed a better mechanical property than their equivalent counterpart. So after validating their phase stability, we try to study their deformation behavior, and for this we jump to the indentation testing. And for the indentation testing, before going, I will say, before going into the details of the indentation testing and the results of it, I want to show some, give the basics of the indentation testing. So, starting with the conventional indentation testing. In the indentation testing, we measure the hardness value, and the hardness value, if you say that what is the hardness, so it is a resistance to permanent deformation. So, how things will work here, like we have a indenter of a particular geometry, and we press the indenter with a static load on the specimen surface, which is flat, and we hold it the indenter on the specimen surface for say 10 to 15 seconds, generate an maintain equilibrium between them, and then remove the indenter. So after removing the indenter, there is an impression made on the sample surface, and we measure this impression, the area of impression in the optical micrograph, and measure the hardness value. So hardness value will be equal to the ratio of the force applied divided by the area of the of the impression made. So if you see the geometry, it's a square shape. This is the impression made on the surface, and if you see the periphery here, so it's a square with a diagonal d, and it is having area of d square, but it's having area of d square, but this area will be equal to d square by 2 into 1 upon sine 68 degree. So sine 68 degree will be the half of this fx angle, and so when we calculate it, it will become 1.855 f upon d square. So although this conventional indentation testing was good, but for a very small load, the impression is very small, so that it cannot be measured from the optical microscope. And if you try to measure it, it will give a little bit error. And also during the unloading part, there is a recovery in this the impression, and then it leads to a minor error in the hardness value. And also this conventional indentation techniques that does not give the modulus value. So we jump to the so it was instrumental indentation was developed with the Oliver Fur method, and what it is, how things work in this instrumental indentation testing. So a indenter of a known geometry was pressed against the flat sample, and during the loading or during the complete indentation testing, the loads and the indentation depth were continuously monitored during the process, and during the unloading, during the loading part, we got a loading curve, we got a holding curve, and then unloading curve. So what is the benefit of it? Like with this, the load indentation curve, and with some set of formula, we can get the hardness and the modulus value. So if you can see that that we have a hardness value, and since we have a indenter is a known geometry. Since we know the geometry of the indenter, like it's a pyramidal indenter, we know the pyramidal geometry. So we know that what is the area of indenter as a function of indentation depth. So then we can measure the maximum depth at the maximum load, and we can, since we know the area function, we can calculate the contact area of indenter with the sample, and we know the maximum force, so we can calculate the hardness value. Similarly, with the indentation modulus, during the unloading part, we can measure the slope of the unloading part this year, and we can relate this slope or stiffness value with the reduced modulus. Okay, the reduced modulus is combined modulus of indenter and the specimen material, and we got the stiffness value, so we can cut this reduced modulus. And if you assume that the indenter and the specimen will behave like a spring in series, so we can calculate the indenter the modulus of specimen. Like this is the formula of calculating the modulus value, and this is the indenter, the modulus of indenter, Poisson ratio of indenter, and we can calculate the modulus value of specimen. So this way we got the modulus and the hardness value. So coming on to the high temperature nanoindentation testing, there is the complexity is involved in the high temperature nanoindentation testing, because if you do the temperature testing at high temperature, there is a chances that metal get the specimen get oxidized, even that indenter tip can react with the material, and that leads to the deteriorating the property of indenter. And also, since at high temperature there is a possibility, then there is a temperature difference between the tip of the indenter and the sample. So what happens then can be there can be a temperature gradient between the indenter tip and sample, and that leads to the thermal drift, and that ultimately result in the value change in the value of hardness. So that can be an accurate. So in order to solve the problem, we took the help from micromaterials. They have a state-of-art technology, that nanotech extreme setup. So where they have used high vacuum of in the range of 10 to the power minus 6 millibar, and such a high vacuum reduce the possibility of sample oxidation. They have high temperature indenter tip, which is boron nitride Berkovich indenter tip, and that this is quite stable for the particular temperature range of 9 to 900 or 1000. And also they have a tip heating setup. Like if you see that during the indentation testing, along with the sample, the indenter tip is also going to be heated. So the temperature difference between indenter tip and the sample will be very negligible, and there's a thermal drift, and the thermal drift possibility of thermal drift, and the error in the hardness measurement, modulus measurement will be low. Also, they are using high indentation load, so the error will be minimum. Along with this, they are using omega band 600 Siemens to stick the sample to the high temperature mount. So that is giving a better stability. So with this high nano extreme setup, we able to measure the high temperature nano indentation. But before going to the nano indentation, I have done a rigorous microstructure characterization and try to find out the grain size and the texture information. And we can see that in the BST image we got a random texture value, and if you see that at room temperature we got a basis structure. And to understand to check the phase stability of this basis structure at high temperature, or almost 1673 Kelvin for 48 hours, we done that heat treatment, and we find out that even at such a high temperature and for a long time we got one single phase structure. So we confirm that this is a single phase structure even particularly at high temperature. So then we jump to the nano indentation testing, and what we have done nano indentation test from 298 Kelvin, 573 Kelvin, 773, 973, and 1173 Kelvin. So we have done a series of indentation tests and at different temperature, and also at a particular temperature we done 5 to 7 tests and to get the average value of hardness and indentation. So from this indentation curve we got the hardness and the modulus value. And to understand the deformation behavior, we have done plotting the hardness as a function of temperature, and you can see here the hardness is pretty high, and this can be a reason of solid solution strengthening of this material, because they have 5 principal elements here, and they are developed by high entropy alloy concept. So the movement of dislocation will be difficult in this alloy. So that way they have a very high solid solution strengthening in this alloy. So if you see that this behavior as a function of temperature, you can see that it can be has a 2 stages, where initially from room temperature 298 Kelvin to 773 Kelvin, there is a steep drop in the hardness value, and then there is a almost a temperature independent behavior. So if you see this steep drop can be a result of there is an activation barrier for the movement of edge and screw dislocation from a locally favorable region. So thermal temperature or thermal assistance is giving the a help to move the dislocation from their locally favorable region. So that's why there is a steep drop in this value. But if you see this plateau region is because there is an equilibrium between super jog pinning and super jog diffusion. So what is super jog? So this is 773 Kelvin, and at this temperature, there is a dislocation line, and in the vacancy can diffuse along the dislocation line, and it can form a super jog. And once it can form a super jog can pin the moment of dislocation, so that way it will increase the hardness value. But at the same time, because temperature is high, super jog can diffuse along the glide direction, and since they are moving in the glide direction, they can relieve some stress. So because of this super jog formation and super jog diffusion, there will be equilibrium between them, and that leads to the temperature independent deformation behavior. So we have measured the hardness value, modulus value as a function of temperature. So you can see that the modulus value is even considerably high, 260 GPa we got at room temperature, and even like a 1173 Kelvin we got to 45. Okay, sorry for this disturbance. Yeah. So we got this value, and when we measure, we got a monotonously decreased modulus value. And if you see the slope, initially the slope is low, but with increase in temperature, slope is also increasing. So in order to compare this modulus value with the other alloys, we use Varchny model, and the alloys which you are studied in the literature, which is hafnium, niobium, tantalum, titanium, zirconium, and niobium, tantalum, titanium, vanadium alloy. So when we compare this alloy with the non-equiatomic alloy, obviously this our alloy is going better, giving the better modulus value. And also if we see the parameter value, and we see that there is a SE parameter and TE parameter. So SE parameter will give you the temperature dependency of young modulus, and TE temperature will give you the resistance to and thermal, it will give us thermal stability. So we can see that we have this alloy has a 31 value of SE, giving the temperature, it is relatively higher temperature dependency, and also the thermal stability is high. This alloy in thermal stability of this alloy is high over a wide temperature range. So after modulus measurement, we got a load indentation curve, and from load indentation curve we can measure the elastic recovery index. So if I am able to define the elastic recovery index, it is a ratio of energy released during the unloading part of the curve to the total energy absorbed during the curve. So if you see that elastic recovery index, it will monotonically decrease as a function of temperature, which is similar to the young modulus variation as a function of temperature. But you see, if the plasticity index, there is this increase in plasticity up to 773, and then there is almost a constant value of plasticity beyond 773. So this behavior is similar to the hardness variation. So we can say that plasticity is behaving like initially the hardness is dropping, the plasticity is in this increasing, and then there is a stable plateau region. So similarly, we have measured the hardness to reduce modulus ratio and yield resistance pressure. So they are also giving the similar behavior than the hardness behavior. So in order to understand deep this material, we done ab initio molecular dynamics simulation. So before going deep into the details of this simulation, I want to give a brief bird eye view of all the methodology available in the atomic calculation, and the computation cost involved, and the accuracy that we get. So starting with the quantum mechanics, the density function theory is the best approach in the quantum mechanics, where electronic and ionic degree of freedom is treated. Actually, it solve the Schrodinger equation and try to find out the wave function, like wave vectors function, but it do it in an indirect way. Like initially it approximate the electron density and the exchange correlation function, and try to find out the energy. So once you get the energy of system, you can calculate the other thermodynamic property. Obviously this is quite include uh, the computational cost, but this will give you very good high accuracy also. And there is another method like the molecular dynamic simulation, where atom is treated as a classical particle, and the motion of the atom are predicted from a interatomic potential, and solving the classical equation of motion, that is the Newton law. If I say the interatomic potential, we need the interatomic potential to do the MD simulation, and this interatomic potential are based on the experimental observation and the empirical formulas of the known forces, like van der Waals forces and the electrostatic forces. So obviously the modern MD simulation may have ability to simulate large number of atom, or a supercell with contain large number of atom, but it give a relatively poor accuracy. And also, since for a new metal where you don't know the interatomic potential, it is very difficult to do the MD. So there is another method called ab initio molecular dynamic simulation. So here the electron are treated fully quantum mechanically within the DFT framework, and once we get the forces from the DFT values, we treat the atom quantum classically. So it will give a accuracy as a DFT, and you can model the large number of atom like 100. So we use this ab initio molecular dynamics approach, and first we develop a random structure of high entropy alloy with a method, or which is called SQS method, special conjugate random structure method, using a tool which is AT, and we develop a you can see we develop this cell, the random super cell, with 100 atom, and with now after once we successfully developing this random structure of 100 atom supercell, we done the ab initio molecular dynamic simulation in the WASP, uh, and try to relax the structure once at different temperature, like we have done the testing in up to 7 temperature, like 5 to 98 Kelvin, 573, 773, 973, and 1173. So we have done the ab initio molecular dynamic simulation at this temperature, and try to relax the structure. Once we got a relaxed structure, we find out the second order elastic constant, and from the secondary elastic constant, we calculate the bulk modulus value and the bulk elastic constant. So we compare this the Young modulus calculated from the MD simulation, ab initio MD simulation, and from the experiment. We got not exactly, the value are not exactly matching, but we got a comparable result. So once we got the second order elastic constant, we try to calculate the anisotropy behavior, and we see that the modulus value is high along this. When we predict this anisotropy behavior, we find out that the modulus is high along 001 direction and low along 111 direction. But if you see the outcome of this thing, like at 298 Kelvin and even in 1173 Kelvin, the change in anisotropy is very minimal. So we can say that the temperature dependency of anisotropy is very minimal for this alloy. So it is showing a better property and better temperature, less temperature dependence. So I can conclude in my talk that non-equiatomic alloy is giving a better thermodynamic stability and mechanical properties compared to their equiatomic counterpart. Their anisotropic behavior is less temperature dependent, and this alloy had better thermal stability. Their hardness values initially dropping, and the reason is because of dislocation are able to move from their locally favorable region with the help of thermal assistance, and there is a followed by a plateau region where there is an equilibrium between superjog pinning and superjog diffusion. So thank you very much. I think Dr. Sam can take over. I will stop sharing.
Thank you very much, Dr. Raturi. So now we will be having a brief presentation from Andrew Burke of micromaterials. On stage now. Okay, so Andy is coming on stage in a moment. So if you could leave stage for now, and we'll all come back on stage after Andy's presentation for the Q&A session. Okay, so leave stage for now, and let me bring your slides up, Andy. There you go. Take it away.
Okay, thank you, Sam. And thank you, Dr. Raturi, for that excellent presentation. Very interesting indeed. So I'd like to finish off today by presenting a few slides on the instrument that was used to generate the hardness and elastic modulus data that we saw in Dr. Raturi's presentation, and that is the Nanotest Extreme. So we had a brief introduction in the previous talk. So in a bit more detail, the Nanotest Extreme is Micromaterials' multifunctional nanomechanical test platform that is designed to test at high temperatures in a high vacuum environment. So with this system, we have two loading heads. So we can apply forces up to 500 millinewtons with the low load head and up to 30 newtons with the high load head. So we have two loading heads, and both of these can be installed on the same system. So we cover the nano range and the micro range. Currently, the maximum operating temperature of the system is 1000 degrees Celsius. So that is, as we saw in Dr. Raturi's talk, we are heating the sample and the indenter up to a maximum of 1000. But we do have an ongoing development project to extend the range to 1200 degrees Celsius. So with this system, we can perform indentation. So that's instrumented depth sensing indentation, all the way up to 30 newtons. We can perform scratch, wear, and friction measurements, and also high strain rate impact tests. And we can do all of those things in this high temperature, high vacuum environment. In addition to that, we can also include a nano positioner on the system. So this is a two-axis piezo stage that allows us to generate 3D images of the sample surface, and also allows us to target very precisely with nanometer resolution, which means we can target submicron features, so things like different phases in superalloys or even grain boundaries in ceramics. And again, that is also compatible with the high temperature capability of the system. So why do we need to use vacuum? Well, this was again mentioned in the previous talk, but two key reasons. Firstly, to eliminate oxidation of the sample, and secondly, so that we can use diamond indenters above 400 degrees Celsius. Therefore, we can use this system to test at higher temperatures compared to an ambient system or even a system that employs gas purge to remove some of the oxygen from the environment. So in terms of sample oxidation, of course, many materials and metals and alloys will oxidize at high temperature, and this oxide layer significantly interferes with the nanomechanical characterization that we are trying to do on the sample surface. So we need a way to overcome this limitation. We can perform the test in a protective gas purge environment, for example, argon purge, which is what we use for our non-vacuum system. We have a purge capability there. And this is sufficient to slow down the rate of oxidation, but it's often not enough for some metals that are readily oxidized, or if we want to perform long duration tests. So you can see in these pictures on the right here, we have a tungsten alloy, so a metal that very rapidly oxidizes at high temperatures. Even in an argon environment, after 1 hour at 750 degrees C, we see extensive oxidation of the surface. After 1 hour in forming gas at 700 degrees, it's not as bad, but we're still seeing areas of oxidation on the surface. However, in a high vacuum environment, as you can see here on the bottom, this is at 750 degrees. After many, many hours, probably more than 12 hours at least, we don't see any visible signs of oxidation. Similarly for the indenter, so you can see here a list of the most common indenter materials. For example, we have diamond, which is will start to oxidize at more than 400 degrees, tungsten carbide 500 degrees, cubic boron nitride 750. Sapphire is inert, of course, being aluminium oxide. But again, sapphire is probably the softest of those 4 materials, so it will blunt more quickly. So on the right here, we can see an AFM image of a diamond indenter after prolonged use at less than 400 degrees C. You can see the pyramidal shape and structure is clearly defined, and that is a nice indenter tip. The image below it is the same indenter after just 90 minutes at 900 degrees in a argon environment. So even in with this protective purge, we see the degradation of the tip. Those faces, the pyramidal faces, are no longer clearly defined, and the tip is severely rounded. So this now is no longer usable for nanoindentation. So again, we need to use high vacuum, i.e. less than 10 to the minus 5 millibar, in order to protect the indenters as well as the sample. So in addition to oxidation, this was also alluded to in Dr. Raturi's talk, we have to consider any potential reaction between the indenter tip material and the sample material. So with nanoindentation, we are generating very high contact pressures. So when we combine that with high temperature, we have the conditions for a possible tribochemical reaction between the tip and the sample. So the most common example of this is when we are indenting steel with a diamond indenter. So as you can see in this SEM on the left. So what's happened here is the carbon in the diamond has been absorbed by the iron in the steel, forming these iron carbides, and that's completely destroyed the tip. Similarly, on the right here, we have another diamond Berkovich indenter, but in this case, we were indenting nickel at 700 degrees Celsius. And again, a similar thing has happened here. The carbon has been reacted with the nickel to form nickel carbides, and our sort of sharp point of the tip is turned into just a flat face. So again, that is no use anymore for nanoindentation. So we do have to, in planning our tests, we have to consider what indenter material we are going to use. So this is a table from a paper by Jeff Wheeler a few years ago, and it summarizes, or it gives an overview of the different indenter materials, the most common indenter materials on the left, versus various sample material types. Okay, and this table was produced from looking at hot hardness literature, and also high temperature wetting and metal ceramic composites. So it's not always a perfect guide in terms of nanoindentation. For example, we have found that performing tests on nickel with a sapphire indenter, aluminium oxide indenter, is okay. So it says here that it may react, but we have found, we've done several tests at very high temperatures on nickel with sapphire, and we don't see any degradation of the indenter. But nonetheless, this still provides a good guide, to work out which indenter is probably the best choice for your material. I mean, tungsten carbide is the most inert with, or most of the sample material types. But again, that's one of the softer materials compared to the boron nitride or the diamond. So these tungsten carbide and sapphire, they're more likely to wear because they're just not as hard as diamond and other types of material. So we have to factor that in when we're performing tests, especially on hard materials. The tip rounding will occur much quicker than it does with diamond. Okay, so I think you should have some handouts that Sam has provided on the right-hand side. So we have our nanomechanical testing to 1,000 degrees. This gives a few examples of high temperature testing. There is a HT high temperature creep resistance app note, which includes some of the or looks at the creep resistance of the high entropy alloy that Dr. Raturi talked about. So there's some more information in there about that. And finally, we have a high temperature publications application note available for you to download. And this includes 76 high temperature publications that have or that include nanotest high temperature data, ranging from 150 degrees all the way up to 1,000 degrees. And these have been grouped into 4 sections. So 3 common uses of the extreme and well, the high temperature capability in general: nuclear materials, PVD hard coatings, and aerospace materials. And then the final section is just other materials with high temperature applications. So this, we hope, will be a useful guide to you, because we have, in addition to the sample type, we've also listed the indenter material and the test environment. So it may provide a useful guide to see if similar work has been done on the samples that you want to test, and if so, what indenter was used, what test environment was used. So that gives you maybe a bit of a head start in terms of planning your tests. Okay, so in summary, the Nanotest Extreme, I think, is fair to say that it's the proven choice for high temperature vacuum nanomechanics. We have a list of some of our extreme customers on the right here. The first system we sold was to the University of Oxford. That was the prototype system, if you like, and that was probably over 10 years ago now. But since then, we've had a number of high-end research institutes and universities that have used the system for the testing materials at these very, very high temperatures. So I think the Nanotest Extreme offers a reliable and high throughput system, particularly well suited to the development of superalloys and high entropy alloys, as we saw in Dr. Raturi's presentation, and other materials that operate in these very high temperature environments. Okay, so that was my short introduction to the Nanotest Extreme. I'll hand back to Sam, and I believe we'll have some time for a few questions.
Thanks, Andy. Yes, we will. So we're at 5 minutes to 1 p.m. in the UK right now. So we have 12 questions that I've marked. So if you're okay with this, and also Dr. Raturi is, we could go just a few minutes over in order to address those questions. Is that okay?
Okay, yeah.
Dr. Raturi, are you okay with that? Running a little over the hour in order so that we address those questions? Excellent.
Yeah,
so I'll begin with those in a moment, but for now, for those people here, let me share the link to the attendance certificate. So please go ahead and click on that, but don't leave. The attendance certificate link it'll last for the whole day. So go ahead and open that, and then come back once we do questions. So I'll begin with the first question that was asked, and then we'll move through like that. So let me move those slides over. Okay, so we got one from Pulami who asks, how is the Young's modulus calculated in nanoindentation?
Okay. So should I share my screen?
Yeah, actually, let me just quickly. There we go. Let me scroll through these quickly, and then.
Yeah, this is fine. So finding out the modulus value, we use the unloading part of the load indentation curve. We took the the slope of the unloading part of indentation curve at the maximum load. We took the slope, and this slope can be related with the reduced modulus, and from the reduced modulus we can find out the Young modulus with this formula. So that's not.
Okay, brilliant. Thank you. Our next question is from Aditya, who asks, what is the material for the 1100 Kelvin indenter probe? So I think that's in another one.
I think micromaterial used boron nitride. If I am wrong, you can correct me. Right. So I think it is boron nitride, right?
Yeah, that's right. Boron nitride. These tests.
Okay. Got it. Thank you. We have quite a few questions here from Dr. Nath. The first one here is, what is the role of single phase? Or I think when you were speaking about the...
So actually, if you answer that, why we need secondary phase in our material. So generally it was used to increase the strength. And since this alloy already have a very high strength, and there is a problem with the brittleness. So if you introduce the second phase, it will lead to increase the brittleness problem in a more severe way. So if we get the same level of strength in the single phase, it's better to deal with the single phase instead of adding the secondary phase, which will increase the complexity and also the brittleness in the material. So that's we are looking for the single phase.
Okay, got it. Thank you. Further question from Dr. Nath, who asks, what is the grain size?
The grain size is, we use the average value grain size, and it is around 200 or 200, yeah, 200 plus minus 30 micron. 220 and plus minus 30 micron.
Got it, thanks. And just to clarify, I guess this is a post-processed EBSD image?
Yes.
Okay. Great. We have another question from Aditya, who asks, what is the strain rate of the impact test?
I think we don't... we have done indentation test.
Yeah.
I think maybe I can talk about the impact test in general terms briefly. So the strain rate obviously depends on a number of factors, but with the impact test on a nanotest system, we're able to pull the indenter away from the surface and release the indenter, so it accelerates to the sample surface with high energy. Typical impact speeds are around 1 to 2 millimeters per second, but with a sharp pyramidal indenter like a cube corner or a Berkovich, we can generate strain rates of 10 to the 5, 10 to the 6 per second. So again, high energy, high strain rate, particularly useful for studying tool coatings. And again, we can do that at high temperature as well. So.
Okay. Thanks, Andy. Another question from Dr. Nath here, who asks, I think he's trying to ask, is there any post-cast treatments applied to the high entropy alloys?
Yeah, we have done the annealing treatment, and at 1000 also we do the the phase stability also we then at 4000 degrees Celsius for 48 hours. But even like 1000 degrees Celsius for 24 hours, it is still a cast structure. So so we are not able to remove the cast structure at 1000, but we are able to remove at 2400 Kelvin. Sorry, degrees Celsius, 1400 degrees Celsius. Yeah.
Okay, got it. Thank you.
And someone is asking for my email ID, so I have wrote in the email ID in the chat. So if you want to contact me, you can contact me after that.
Okay, great. I'll unmark that question. Thank you. So yeah, that's in the chat for anyone to look at. A further question from Dr. Nath, who asks, what is the accuracy of simulation compared to actual results? So I guess
the value is, we can say that value is with the experimental, we got deviation is a little bit high, I will say if it is not one-to-one matching, because there is a ab initio MD, you need to find out the exact correlation function, and even with this experimental testing, we are indenting very small material, so there is an isotropy effect. So there are variation is large, but we can say that there is a variation is because of this material property, the anisotropy and the other things, the simulation also.
Okay, thank you. From Dr. Nath again as well, and ask, has any work been done on high temperature tribology of this material?
Tribology, I don't. It is not in my like contact. I don't know. Maybe somebody has done recently. Till now, I don't know.
No, that's okay. I guess.
So add to that, we can perform high temperature tribology with the Nanotest Extreme system. So we have single pass or scratch testing, and also a number of reciprocating wear techniques that we can do at high temperature. It's just a general comment.
Okay, thanks, Andy. Okay. Question from Dr. Nath about creep. Any creep studies done on this material? I guess Andy can also comment on creep using the Nanotest platform as well.
Yeah, sure. In one of the handouts is related to high temperature creep. So there is we have looked at creep resistance of this alloy and compared that to other methods other materials, which candidates for high temperature creep resistance. So you can find out more in that PDF handout.
Okay, so for anyone who hasn't downloaded those, they're in the handouts tab, so you can find those there. Thanks. Okay. I think a question for you, Dr. Raturi, from Dr. Nath again. What about chromium carbide formation on high entropy materials?
If the refractory entropy alloy has a chromium in it, there is a possibility of chromium formation. Like chromium can be react with the other metals, but we don't have the chromium in our metal, so there is a chances. No, there is no chance. But if there is a chromium, there is a possibility.
Yep. Okay. Thank you. Another question from Aditya here, who says, please comment on the life of the indenter against steel at 900 degrees Celsius. More like hours or minutes per contact cycle, or hours?
I think more like minutes. I think at that temperature. The contact area is very small, so of course the geometry of the tip is very important. So any small change renders your data fairly meaningless. So I think it would not last very long at all in terms of meaningful nanoindentation.
Just further on from that, Andy, what sort of calibration frequency would you recommend for high temperature indentation tips? Would it be before any indentation cycle?
Yeah, basically before and after every indentation cycle. Certainly if it's a relatively hard material, just to keep track of the tip shape. We have even mounted a calibration sample such as fused sticker along with the sample tested during a high temperature schedule, so we can perform reference indents between temperatures. That's not always really necessary, but it is important to keep track of the tip geometry when doing tests at very high temperatures.
Yeah, absolutely. Yeah, definitely key to keep track of that, because really without it you have no usable results, as you said.
Yeah, absolutely.
Okay. A question here from Suyash, who asks, what is the required surface condition for nanoindentation? I guess roughness, any preparation before nanoindentation that is recommended?
Yeah, I mean, generally speaking, in terms of nanoindentation, the lower the surface roughness, the better. I think the ISO standard states that the surface roughness should be 20 times lower than the maximum indentation depth.
Mhm.
So the maximum indentation depth 20 times the RA value. That's not always possible, but generally speaking, flat and as smooth as possible, especially for testing at very high temperatures. At room temperature, you don't have as many restrictions in terms of number of indents, just form a large number of indents. But as we said, tip wear is more of an issue at very high temperatures. So you want to try and limit the number of indents you do. You can't really do like hundreds of indents where, at very high temperatures where you might do that at room temperature. Therefore, for testing at these very high temperatures, I think you do need to pay particular attention to surface preparation to get it as good as you can.
Okay, thank you. A question from Chandra here, who asks, in the case of a multi-phase surface, how can we measure the hardness with a nano-indenter? I think they're trying to ask about determining the hardness of different phases across the surface.
So we can do that with, I mentioned it in my first slide, we have this nano positioning stage, piezo stage, which allows us to generate 3D images of the sample surface on a micron scale. So we have done this with various multi-phase materials. For example, a nickel superalloy. We have the sort of 2 phases, the matrix and the precipitate phase. These can be, sort of micron scale features or even submicron scale features. But once we've generated these 3D images, which may just be a few microns in area, we can see as long as we can see the different phases, we can target indentations within those phases. Because with the piezo stage, we have nanometer resolution positioning. Okay, so much better, much more accurate compared to any standard mechanical stage, and that means we can target indents in these different phases very, very precisely, and therefore independently measure phases of these different phases. And again, we can do that at high temperature as well. So there was a paper published, I think last year or a couple of years ago by NPL. They used our system to test individual grains of, I think it was like a cobalt chrome material. So again, I suggest that will also be in the high temperature publication application of that paper. So if you want more information, you can find that.
Okay, thanks, Andy. Getting towards, so we've got a couple of extra questions here. So that final one from Pulami I'm going to take as the final question. So I have 3 remaining. We'll answer these, and then we will wrap up the webinar. Okay, so the first question from Pulami, they ask, what melting method did you use to synthesize the high entropy alloy?
We use vacuum arc melting method. That was the method. It's a vacuum arc.
Okay, got it. Thank you. Nilesh asks, for atomistic simulation, which potential did you use?
Power potential. Pause ZW.
Okay.
Purdue, I forgot the full form. It's PAW underscore ZW. I have to figure out maybe.
No problem. Do you want to put that in the chat and I can think?
Oh, sorry. Project Augmented Wave.
There we go. Great. Thank you very much. And now the final question from Huami. Are homogenization treatment and heat treatment at 1673 Kelvin different?
Yeah. We for annealing, for homogenization, we done at 1000 degrees Celsius for 24 hours, and for checking the phase stability, we have done it 1400 degrees Celsius for 48 hours.
Okay, fantastic. Thank you. So I think with that, we will draw the webinar to a close. So just want to say thank you very much to everyone in the audience for listening and for asking such great questions. It was, yeah, I definitely learned a good bit today as well. So thank you very much, Dr. Raturi, for your great talk, for answering all those questions. Thanks, Andy, for providing great information about the Atomistic stream system. Whilst we wrap up, I just want to say, please do go and visit the Micromaterials website for more information and the Micromaterials LinkedIn page. So the LinkedIn page is very application focused. You're not going to get a lot of sales and marketing things. You'll find out very much the technical information that we shared in this webinar. After this, you will all receive an email with a link to watch the replay, and also some information in that email about contacting Micromaterials about further information. So if please do get in touch if there's anything you want to ask. So with that, I just want to say to everyone, hope you have a great rest of your day. Thank you very much for being here.
Thank you.
Okay, thanks all.
Thank you, everybody. Thank you for joining.
Okay.
Bye-bye.
Bye-bye.
Bye.